So now let us do some theory. Okay. So note that when you have K over F as a field extension, you all know what is the definition of vector space, right? Vector space over R. The same definition, when you replace the scalars with some other field F, it becomes a vector space over F, over the field F. Okay. So when K over F is a field extension, K is actually a vector space over F. Okay. Check this. It is a vector space over F. The same properties of a vector space over R when you replace the scalars in R by scalars in F. So the upper field is a vector space over the lower field. Extension field is a vector space over the base field, always. Okay. And therefore, we'll define the degree of the extension to be just the dimension of K as an F vector space. Okay, we'll denote it as K colon F, and it's denoted to be the dimension of K over F. Right. So the first thing that we see about these dimensions is this. Let K over F be an extension and alpha be an algebraic. Okay. Therefore, first of all, square bracket and round bracket now no longer make any difference. Okay. The set of all polynomial functions in alpha is the same as the set of all rational functions. Anyways, there's a containment here. Polynomial functions are rational. Every polynomial function is itself divided by 1. But every rational function in fact turns out to be a polynomial function. Then alpha is algebraic over F. Okay. And both of these are in fact isomorphic to Fx mod the ideal generated by the minimal polynomial of alpha over F. Okay, that's why we were looking at the smallest degree monic irreducible, because we wanted to take the quotient and we want a field, right? So when it's irreducible and you quotient it, you get a field. Correct? So this is one thing when alpha is algebraic. Second thing is the fact that F round bracket alpha, it's a field over F, so it's a vector space over F, right? And if you say the degree of alpha over F is n, then n itself is the dimension of F alpha over F. The dimension of F alpha over F is exactly the degree of F over F, degree of alpha over F. And what is the basis? Well, just take 1 alpha squared up to alpha n minus 1. Monomials in alpha up to degree n minus 1. This is an F basis of F alpha over F. Okay. So there are two statements that we prove here. One is a description for F alpha in terms of quotient, and the other is a basis for F alpha in terms of alpha. All right, so let's look at the proof. Proof is again in the larger lecture notes that we'll see. So this is proposition 2.7. So let's look at that. So this is what we need. Okay, K over F is field extension, alpha and K is algebraic. Little fx they denote as the minimal polynomial, and n is the degree. The minimal polynomial, which is the degree of alpha over F. Okay. Square bracket is equal to round bracket for F alpha, and this is isomorphic to Fx mod minimum polynomial. Degree is n, and 1 to alpha raised to n minus 1 is an F basis. So why is this true? Okay. So now consider the normal homomorphisms called substitution homomorphism, which is take any polynomial in fx and substitute x equal to alpha. That is an element in f alpha, right? So psi of x is equal to alpha extended linearly to all polynomials, and psi of identity. And further, what do you note here? Alpha is an element in K in outside. Okay. Therefore, all the elements of F will actually be fixed because any polynomial expression that involves only little f, it has no alpha, so there is no substitution there. Therefore, psi restricted to small f is in fact just the identity map. Okay. Elements of f get fixed. All right. So what is a kernel? The claim is kernel is the minimal polynomial. Okay. Why is that? Any idea? We're trying to show this statement. Why is this? They've already seen an argument in the morning and probably even before. Sorry, not today morning, but before. That's why I'm asking. Why is kernel equal to ideal generated by the minimum polynomial? So what is the kernel? Kernel is a set of all polynomials which, when you substitute alpha, they become zero. So up to scalar multiplication is a collection of all monic polynomials which vanish when you substitute alpha. Now there is a unique monic irreducible polynomial which, when you substitute alpha, becomes zero, the minimal polynomial. And every other polynomial must be a multiple of that. We just saw that in the proof of the unique monic irreducible polynomial. Exactly the same proof. Repeat the same argument. Okay. Therefore, kernel is generated by the irreducible polynomial, monic irreducible polynomial, which vanishes at alpha, which is precisely the minimal polynomial of alpha by definition. Okay. So that is the kernel. And now kernel is what? It's irreducible, so kernel is maximal ideal, right? So fx mod little fx, which is the minimal polynomial, this is a field. Now there are two things. This is a field, okay? But by isomorphism theorem, fx mod this kernel is isomorphic to f square bracket alpha, because this is a surjective map. Any polynomial expression f square bracket alpha, take the corresponding polynomial. So this is a surjective map, right? So this quotient is isomorphic to f square bracket alpha. But the irreducible polynomial we are quotienting, therefore this quotient is in fact a field. So f square bracket alpha is a field, but f square bracket alpha is trivially contained in f round bracket alpha. Because here we have polynomials and here we have rational expressions. The rational expression contained in f's round bracket alpha, we know that this is a field. But now just check that this is the smallest field that can contain both, because any polynomial f of x which is non-zero, one should be able to invert it and take 1 upon f of x, right? So if this is a field, and this is definitely the smallest field containing the first one, then both of them have to be equal. Is that okay? So since this ideal is maximal, f square bracket alpha is a field, and so these are equal, because F round bracket alpha is the smallest field containing F square bracket alpha. Okay. Now let's go to the second part. Second part says that if n is the degree of alpha over f, then the dimension of f alpha over f is n itself, and 1 to alpha raised to n minus 1 is an f basis. Okay, let's do that again. So now let g alpha be any polynomial expression in f square bracket alpha. Okay, look at the corresponding polynomial gx. Right now, gx. Now this divide this by the minimal polynomial of alpha. Okay. So gx is sum fx times qx plus rx, where qx is the quotient, fx is the rx is the remainder. But what is the specialty about division algorithm? The degree of the remainder must be less than the degree of the quotient of the dividend divisor, right? So degree of r must be less than the degree of f or the monic polynomial, or else it should just be the zero. Okay. Therefore, what do you get? When you substitute alpha, g of alpha is f of alpha times q of alpha plus r of alpha. But f of alpha is 0, so g of alpha is r of alpha. Got it? So g of alpha as a polynomial expression in alpha is in fact just equal to r of alpha. But rx is what? Degree of rx is less than degree of fx, or rx is 0. So whenever it's a non-zero polynomial, its degree is at most n minus 1. Because degree of the minimal polynomial of alpha is n, right? So R alpha is in fact just an expression in these monomials, 1 alpha to alpha raised to n minus 1, right? So every g alpha in f alpha can be written as some R alpha, and therefore f alpha is generated by 1 alpha raised to 1 alpha alpha square up to alpha raised to n minus 1 only. This much is enough. So this is a spanning set. Now we want to say that it's a basis, so let us also prove linear independence. Okay. So now suppose we have a linear combination summation I alpha ai alpha raised to I. If this is a non-zero linear combination, then this is a then the corresponding polynomial summation ai x raised to I. It's a non-zero polynomial of degree at most n minus 1 that vanishes at alpha. But n is the degree of alpha. N is the smallest degree of a monic polynomial that vanishes at alpha. Right? So this is a contradiction, because if these are all non-zero, this scalar combination is a non-zero combination, then this gives you a non-zero monic polynomial of degree less than or equal to n minus 1 that vanishes at alpha. That is not possible. That cannot happen. Right? Therefore, this linear combination must be 0. Therefore, these elements are linearly independent. Therefore, 1 alpha alpha square is in fact the basis of f alpha over f. And therefore its degree is n. There are n elements here, which is just the degree of alpha over f. Is that clear, everybody? Let's look at this argument and tell me if something is not clear. All right, no doubts. So let's go back. Okay. So if K over F is a field extension and alpha is algebraic over F, then square bracket or round bracket alpha doesn't make a difference. They are both equal. And in fact, this field F alpha is isomorphic to the polynomial ring Fx mod the irreducible polynomial, the minimal polynomial of alpha. And the degree of F alpha or the dimension of F alpha over F is equal to the degree of alpha over F. And a basis is 1 alpha alpha square up to alpha raised to n minus 1. Okay. So some more properties about this. Okay. So if K over F is a field extension, this is the next statement, and alpha is algebraic, then F alpha over F is in fact an algebraic extension. Do you understand the statement? If K over F is a field extension and alpha in K is algebraic, then we know this field F alpha, which has dimension equal to the degree of alpha over F. So this has finite degree. In fact, this field is algebraic over F. This is an algebraic extension. So not just alpha. Alpha clearly belongs here, and alpha is algebraic over F. But every element in F alpha is algebraic over F. That is what this says. If alpha is algebraic over F, then every element in F alpha is algebraic over F. Okay. This is the immediate next statement. It's an easy proof. So this is proposition 2.8. Okay, very easy proof. And short proof also. So just take any other element beta. Take any other element beta in F alpha, which is non-zero. Zero you don't have to consider. We know that alpha is already algebraic. Right? Now what is the dimension of F alpha over F? That is equal to n, which is the degree of alpha over F. Right? So if I look at the set 1 beta beta square up to beta raised to n, how many elements are here? There are n plus 1 elements here. So any set of n plus 1 vectors in an n-dimensional vector space is linearly dependent. Correct? It contains a basis always. This you should know from linear algebra. If the dimension is n, any set of n plus 1 vectors is linearly dependent. Okay. So there exists some scalars a0 to an such that not all 0, such that the linear combination is in fact equal to 0. But do you see then, since the scalars are not all 0, this gives us a non-zero polynomial. And you can just divide by the leading term and you get a monic polynomial. Get a monic polynomial of degree less than or equal to n, which vanishes at beta. Therefore, beta is algebraic. But beta was some element. This is true for all beta in F alpha. Therefore, F alpha over F is an algebraic extension. Is this proof okay? It's a very simple proof. Are you able to follow?
Yes.
Okay. So now for some time we will be having just theorems and theorems. Okay, so this is how the subject is. So there are three more theorems that we before we go to the next topic. Okay, so we have completed this much. Right. So let's go to the next thing. So you remember at one point of time we were looking at maps between two fields such that the elements of the smaller field were fixed. Okay, so we have just given it a name now. So let K over F be a field extension and A, B be subsets of K such that F is contained in both. Okay, F is the smallest, A and B are larger than F, and K is the largest. Then any function from A to B, we will call it an F function. F function if it fixes every element of F. So it will change elements only if the element is outside A or outside B. Okay, so it's an F function if phi of x equal to x for all x in F. Okay. So this just makes it easier to describe something. Okay. So now if K over F is a field extension and alpha and beta are two algebraic elements, it should be alpha, beta in K. So that is a printing mistake. So if alpha, beta, and K are algebraic elements over F, then the two things are equivalent. Okay. If two elements are algebraic over F, one can always ask when is the minimal polynomial the same, right? Is the minimal polynomial of alpha equal to the minimal polynomial of beta? Well, the minimal polynomials are equal if and only if there is some F isomorphism psi. So there is some isomorphism between F alpha and F beta which fixes F such that alpha is mapped to beta. Okay, if and only if there is an F isomorphism psi such that F alpha is isomorphic to F beta, but the map also takes alpha to beta and fixes all elements of F. Okay, then the minimal polynomials are the same and converse is also. Okay, you understand the statement? So let's look at the proof. This is the next theorem. Okay, 2.9. Right, again a short proof. So alpha beta are algebraic over F. So let little fx and little gx be the minimal polynomials, okay, of alpha and beta respectively. Yeah. Now consider this map psi from f alpha to f beta. By how do you define it? Well, for any polynomial expression here, substitute beta in place of alpha. That gives you a polynomial expression in beta. Okay. In fact, rational expression, but both are algebraic, so round bracket is the same as square bracket. So you might as well consider only polynomials. You don't need to consider rational functions. Alright. So this map is always defined. You can always take a polynomial expression in alpha and convert it to a polynomial expression in beta by replacing every presence of alpha, every power of alpha with the corresponding power of beta. Okay. So this map, when applied to the minimal polynomial of alpha, what happens? If f is the minimal polynomial of alpha, f of alpha is 0. So when you apply psi to f of alpha, it is psi of 0. Psi of 0 is 0 because psi is a field isomorphism. Right? Psi of 0 is 0. But psi of f alpha is f beta by definition. Okay. Therefore, f beta is 0. But f of x is a monic polynomial, monic irreducible polynomial. Right? So this is a monic irreducible polynomial such that it vanishes at beta. But monic irreducible polynomials which vanish at an algebraic element are unique. Right? Irreducibility forces it to be unique. Therefore, f of x is equal to g of x by uniqueness. This is just extra that they have written that gx divides fx and therefore fx divides gx by looking both sides. But we have already seen that monic irreducible polynomial vanishing at an algebraic element is unique. So directly you can say that f is the minimal polynomial of beta. But the minimal polynomial of beta is gx. So fx must be equal to gx. So what have we shown here? The minimal polynomial of alpha is equal to the minimal polynomial of beta. Now converse. Converse, now you just have to use what we have done before. Okay. If the minimal polynomials are the same, then we know that these are algebraic elements. So the field f alpha is isomorphic to fx mod minimal polynomial of alpha. But this is exactly equal to the minimal polynomial of beta. So this as a field is equal to fx mod the minimal polynomial of beta. And therefore it is isomorphic to f beta because beta is also algebraic. Right? And both these isomorphisms are f isomorphisms because elements of little f, the base field, are not at all moved. Only alpha gets replaced with beta and beta gets replaced with alpha when you go from one side to the other. So f alpha and f beta are just f isomorphisms. Right? Okay. So the statements seem a little bit complicated, but the proofs are very, very simple. We just need to understand some basic stuff, and then these become very obvious statements. They're using some very, very simple properties of algebraic elements and their polynomials, nothing else. The property that you always use about algebraic element is that there is some monic irreducible polynomial that vanishes. Property that you use about minimal polynomials is that they are monic irreducible, and in fact, for the element that they correspond to, they are in fact unique. There is no other monic irreducible polynomial that can vanish that one. It is a unique such polynomial. There can be other monic polynomials, but there cannot be an irreducible monic polynomial that is different from the monic polynomial. Okay, that's all that you're using here, nothing else. Okay, so let's go to the next. So this is all that we're doing. Okay, we have to complete this. So there are two more theorems, and we will be done for today. But I want you to go back and revise these and try to understand. Okay, I'm going slightly faster, I think. So you have to go back and you have to go through these things. So before we meet next time is tomorrow, I think. Let me just check. So tomorrow's timetable, नितिन सर का क्लास फ्री है क्या?
हाँ सर, शायद, क्योंकि सर ले सकते हैं।
मुझे कैसे पता चलेगा फिर?
वो पूछना पड़ेगा ना उनसे।
हाँ, पूछ के मुझे बताइएगा कि ये लेक्चर फ्री
ओके।
और अभिजीत तो शायद ले रहा है ना?
हाँ हाँ, उनका है लेक्चर पक्का।
और सलीम सर का क्लास
फ्री।
ओके. सो tomorrow's timetable is better. Okay, तो अगर नितिन सर का फ्री है, I want to find it out. Okay, so अगर नितिन सर का फ्री है तो कल we can continue with Python for longer and सलीम सर के क्लास में हम अलजेब्रा करेंगे. ठीक है?
ओके सर।
Okay,
सर
so
8 o'clock हो क्या?
मैं बताता हूँ. अगर मुझे थोड़ा जल्दी कहीं जाना है तो 7:45, नहीं तो फिर 8 o'clock. So that depends. I can only say tomorrow morning देखता हूँ या फिर आज रात तक बता दूंगा.
ओके सर।
Right. So that's it. So कल anyway सलीम सर की क्लास में अलजेब्रा होगा. So before tomorrow's class, try to revise everything that we have done so far. Okay. It might seem lengthy, but it is not too much. There are only 2 or 3 basic things that you need to know. What is an algebraic element? उसका consequence क्या है? Minimal polynomial क्या होता है? Okay. Irreducibility क्या होता है? बस very very basic properties. If you know these, then you know these theorems. Okay. It is not difficult. So let us complete this. Now, let's look at two extensions, K and K prime over F. Okay, two field extensions K and K prime over F. And what do we know? They are isomorphic, but stronger than that. There is an isomorphism between K and K prime, which fixes every element of F. Okay, now you understand what is an F isomorphism. Okay, K and K prime are both lying above F, but every element of F is fixed. Elements of F go to themselves, other elements go to other elements. Okay, and this is an isomorphism between K and K prime. Then what this says is, if alpha in K is a root of a polynomial F, then the image phi alpha must also be a root of the polynomial F, because this is a polynomial over the base field capital F. Okay, if you take any polynomial over the smaller field, and if alpha over one of the larger fields is a root, then its image under this isomorphism is also a root. Okay, why is this? Extremely simple. Okay, I've written it here. In fact, if I've written a proof here, then it's usually very simple, or it is missing from the notes. In this case, I think it is missing from the notes. So I've written it here. So let us start with an expression for this polynomial, right? If it is a zero polynomial, then there is nothing to be proved. Every element is a root, technically. Okay. So let's start with a non-zero polynomial, and let's call it f of x equal to this expansion, summation over I, ai x raised to I going from 0 to little n. N is some integer. Let's assume that is the degree of this polynomial. Okay. Now psi is an f isomorphism. It fixes elements of f, and this is a polynomial over f. So all these coefficients are over f, right? So the image of this polynomial under this map, what is that? Psi is a ring homomorphism, right? If it's a field of if it's a field homomorphism, it's a ring homomorphism. If it's a field isomorphism, it's a ring isomorphism, right? So just pass this polynomial under phi. The 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 polynomial will split the sums, and it will also split the products, because it's a ring homomorphism, right? So it doesn't matter what x be, it will just split through all of these sums and products. So psi of f of x is just summation psi of ai x raised to I, but that again splits into psi of ai times psi of x raised to I, and psi of x raised to I splits as psi of x whole raised to I, because it's a ring homomorphism, right? Field homomorphism is a ring homomorphism. Okay, so psi of f of x is just this. Is this clear why it splits? Because it's a ring homomorphism. Property of ring homomorphism. Okay, so psi of f of x is just summation over I psi of ai times psi of x the whole raised to I. But this is an F isomorphism. So F ring homomorphism. Therefore, elements of F are fixed. AI are elements of F. So these are fixed. So psi of AI is just AI. So psi of f of x is just summation over AI times psi of x whole raised to I. Therefore, these coefficients are the same. So this is now f of psi of x. If you just look at the expression, if f of x is summation over AI x raised to I, and summation over ai psi of x whole raised to I is just f of psi of x. Okay. So psi of f of x is equal to f of psi of x. That is what we have proved here, right? By the property that psi is a ring homomorphism. Therefore, what do we know now? Alpha is a root of f. So f of alpha is 0. So let's plug it here. If f of alpha is 0, psi is a homomorphism. So psi of f of alpha should be 0 because it is psi of 0. Therefore, now look at the other side. Therefore, f of psi of alpha should be 0. Right? So f of psi of alpha is psi of f of alpha, but f of alpha is 0. So this is psi of 0, which is 0. So what have we shown? Psi of alpha is a root of f of x. Okay, that is precisely what this is saying. If alpha is a root, since the homomorphism preserves the elements of f, even the image of alpha, which is psi of alpha, is also a root of the same polynomial because of this property. Alpha was a root of f, and therefore now even psi of alpha is a root. Because psi of f of x is equal to f of psi of x. All right, simple proof, right? Very, very simple proof. We're only using the property that psi is actually a ring homomorphism. All right, you don't really need that this is an isomorphism in this case because you're not looking at pre-image at all. This will hold true for any homomorphism from K to K prime. But we usually work with isomorphisms because we want to compare two fields and understand when they are isomorphic and not. That is why we are only discussing isomorphisms. But this whole argument will work even for any homomorphism from K to K prime. Okay, that should be clear from the proof. We are only using the fact that psi is a homomorphism. We are not really using the fact that psi is an isomorphism. But it should fix elements of f. That is important. Otherwise, you cannot replace psi of ai with ai. This is the most important step here. It fixes elements of f. Therefore, you can replace psi of ai with ai. All right. Okay. That was a simple result. Now let's go to the final simple result for today. Okay. So this is the end. I don't have any more slides. So final simple result for today. Let K over F be a field extension and alpha be algebraic over F in K. If beta is another element which vanishes at the minimal polynomial of alpha, then the minimal polynomial of beta is equal to the minimal polynomial of alpha. We have actually seen this in the proof of the previous theorem, in this proof of this theorem already. Okay, when we went from A to B, A implies B, you took this isomorphism and then proved that we proved that beta vanishes at the minimal polynomial of alpha, but it is monic and irreducible. So the minimal polynomial of beta must be equal to minimal polynomial of alpha. Okay, we have just separated that out as a different theorem because it's an interesting statement. Okay, so once again, let me show you the proof of this. It's just a revision now. Okay, so by the given condition, beta is an element such that the minimal polynomial of alpha vanishes at beta. So beta is algebraic over F because minimal polynomial of alpha is a monic polynomial. But the minimal polynomial of alpha is monic and irreducible. And there is only a unique monic irreducible polynomial for every algebraic element. Right? We have shown that. Therefore, the minimal polynomial of alpha must be equal to minimal polynomial of beta by uniqueness. Okay, we have already proved this much earlier. Any monic polynomial that vanishes at beta must be a multiple of the minimal polynomial of beta. But if you impose it as irreducible, then it must be equal. Right? So by uniqueness, the minimal polynomial of beta is equal to minimal polynomial of alpha. We did prove this as it is exactly like this in the proof of this theorem for one side. But this is an interesting statement on its own. So this is a separate statement. Okay. And we just revised the proof. Okay. So this is what I have for today. So we will stop here and we will do some more things about extensions tomorrow. Okay, so now we are ready. So I will post these two PDFs now in MS Teams. Abhi 5 minutes mein kar dunga. What I want you to do is revise through these before we meet tomorrow in Salim Sir's class. Okay, there we will continue with more stuff. Okay, I want you to revise because otherwise you will start getting confused. So far we have seen many statements, but those only involve two definitions. What is an algebraic element? What is a minimal polynomial? But now we will have many other things to come. So you have to be completely clear about things that we have seen so far. Okay. So revise this before we meet tomorrow. Abhi मैं notes डाल दूंगा. You have one full day. So revise before you come. So that's all. I'll stop here now. Any doubts? Anybody? Okay. So